Hello student, welcome once again in the series of basic ultrasonic testing.
In the last lecture, we just talked about the EMAT, that is electromagnetic acoustic transducer. So when that is used when we do not want to use a couplant. Okay. So now just we talk about in that lecture the selection of frequency. That is most important part. So before going to selection of frequency, I just want to show you that particular image that is shown in that particular slide. So if you see, there is a and on the x-axis there is a transducer frequency, that is the frequency. So on the y-axis there is a wavelength. So when we increase, if you see in that particular graph, when we increase the frequency, at the same time if you see that the red color, that show the penetration. So when we increase the frequency, the penetration is low. Okay, but at the same time when we increase the frequency, the resolution is high. So that means that two parameters is most important when while we selecting the frequency. So first we talk about the low frequency. Actually, that is a problem in ultrasonic testing when we go for testing a particular sample. So maybe in that sample, two defects are present that is near to each other, close to each other. So when the signal come back after the back ball, maybe there is a possibility the defect to close to each other. Maybe the signal of one defect is having a high energy or high intensity of peak. So maybe the second one having a low intensity of peak, or maybe that energy is low. So maybe that these two signal is merged to each other and coming on a display screen as a single. Okay, so that is the big issue. So if we use for a low frequency, so we just talk about, so in case of low frequency, the penetration is high, as you see on that particular graph as well. That means the attenuation is also a lower. So that means high intensity of peak is generated. Okay, so at the same time the resolution is low. So the resolution is nothing but it is the ability of a probe to detect two flaws that is close to each other. So in case of low frequency, that is not possible to find out the defect signal that is close to each other. And for a high frequency, this is just the opposite of our previous case, that is for low frequency. So in case of high frequency, the penetration is low. So the backball signal which are coming out, they will be lower in intensity compared to a low frequency wave, because in this case, due to lower penetration, the attenuation is also high, but the resolution in this case is much better. So like in the previous case, if you have the same scenario, two or three defects lying very close to each other, then you will get two distinct or three distinct echo corresponding to two or three different defects which lie closely to each other. If you talk about the previous case, if we see in previous case, the signal is overlapped because in low frequency signal, they are merged to each other. But in that case, there is not happening this type that overlapping. So high frequency could gives you a high resolution at a low penetration. So that means this is also tell when you want to do. So when you want to do that close surface analysis by ultrasonic testing, then we uh, we are going for a high frequency. Okay, because in that case the penetration will be lower. But at the other end, if you want to check or if you want to go that inspection in depth, so then we should select that particular lower frequency, because in case of lower frequency the penetration is higher, so it would be able to go to the depth that you are looking for. So so how, depending on what exactly you want to do and what kind of defect you are expecting, if you have some idea beforehand, then based upon this penetration and the resolution expect, you can select either a high frequency or a lower frequency. Okay, So when you talk about the defect signal or the detectability of a defect, then one parameter come into the picture, which is known as signal to noise ratio. So that is written as the S by N. So the idea is to minimize the noise so that the signal intensity from a defect is increased. And often a signal to noise ratio of 3:1 is needed as a minimum requirement. And this particular parameter, it will depend on several factors related to probe and the material. So if, for example, if we take that example, if you decrease the lateral beam width, so that means if you have a focus beam, then the detectability of the defect or the signal to noise ratio will be more. Okay. Similarly, if we decrease the pulse duration, okay, which means it is a short length or shorter pulse, then again the detectability would be better. So if you have a shorter pulse, the detectability is better, and it is the signal to noise ratio or detectability is directly proportional to the size of the flaw. Okay, so which is obvious, larger the flaw, better would be its detectability. And if the density of the material is higher or the velocity of sound wave in the material is higher, then the detectability goes down. Okay, these are the main parameter on which that particular detectability has depend, and how we control that increase the detectability or control signal to noise will control the detectability of particular flow. A very important aspect of ultrasonic testing, which is about calibration, that is most important for any testing. The equipment, that the component we are using for testing should be calibrated. Otherwise, when we going for the testing, there is a number of error are generated in the result. So in case of ultrasonic testing, two type of calibration we are using mostly when we talk about the normal probe. One is the distance, and another one is the area. Where area, why we are choosing the area? Because the intensity of the echo depends on the scattering area, or the area of the interface, or the area of the defect which is scattering it. So therefore the area also has to be calibrated, so that you would be able to get some idea as to how big is the defect, whether it is a big defect or it is a small defect. So the distance calibration and another is area. So these are known as distance amplitude calibration or distance amplitude correction, and the area amplitude correction respectively. These are the two primary type of calibration that you do for the normal probe. So in case of normal probe, distance amplitude calibration or distance amplitude correction or area calibration. So in case of distance calibration, the metal distance was varied, and in case of area calibration, the area of the holes was varied, so that get different distance in one case when vary the metal distance to calibrate the distance, and in the case of area calibration, you vary the size or the area of the hole and get different areas to calibrate in terms of area. So that was about calibrating normal probes. But in case of angle probe, because sometimes we are using angle probes when we going to the testing a sample in a that sample in a some angle, maybe that defects are present in some angle, so we are using an angle probe. So that is also a need to calibrate the angle probe. Use a block which is known as second W block, and in this block have several type of features which can be used to calculate the angle, or we can say that we just talk about the calibration, so we use to calibrate the angle for a particular angular transducer. And on the block we also had this angle scale graduated. Okay, and with the help of that scale angle, we could calibrate the angle, and apart from this, we also with the help of the second W block, we also find out the important parameter like the resolution, dead zone, and in fact, you would also be able to get some idea about the sensitivity. So these are the different things that can be done with the help of second W block.
So in ultrasonic testing, we are using different kinds of display where we use ultrasonic testing. So out of which I am defining two or three. So most commonly used display in terms of the amplitude and time that we have seen in the previous slides or maybe in previous lectures. So that particular display or the particular skin is known as A. Okay, that is display in terms of amplitude and the time. So other than these two, we will just talk about the B skin and the C skin. So let us talk about the A skin. So in A skin, as you saw in that particular PPT image, plotted amplitude is plotted against the time or depth, and if you see the signal in terms of a deflection of the time base or a peak, as that shown in that particular image one. So this is a skin. So this is one dimensional view of the defect as shown in that particular skin on the display. Okay. So now we just talk about the second type of skin that is also most important for us, which is used generally in ultrasonic testing. That is a B skins. So in this case, this gives us a 2D profile of the defect, and the display is basically an imaginary section through the sample where we see both the back and the front surface as well as. So at what depth the defect are lying when the defect echo appears on the display. So that is how it's generate that 2D profile of the defect. If we look at the particular display which is shown in that image on that particular slide, the display the time or the depth in this case now will be in the y-axis. Okay, and because the depth will be directly shown on the display, and the x-axis will be skinned distance. So uh, how this will show on if shown on a fluorescent screen. uh, so if there is a defect echo or as a fluorescent point coming into the display and staying there for some time, so that you have enough time to see and visualize them. So let us say we have a sample as shown that particular image on first image, and that having two defects as you see in that particular image B and C. Okay, so two different depth. If you see in that image, the B and C are both are the different defects and both are placed in the different depth. So so with the help of probe, we just move probe throughout that surface so that ultrasonic waves are generated throughout the sample. Okay, so the moment it goes over these defects, then coming into the display at a particular depth, as we see on that particular image. Uh, we already told that this is an imaginary section through the sample where we can see the depth, where you can both the front face and the back face, or you can see that other display 2D view. So this will come as a fluorescent points on a phosphor screen. So instead of the oscilloscope screen that you have in case of A skin, if you see that there's a oscilloscope screen are using case of A skin, you have a phosphor screen in that B skin where the defect signal will come and fluorescent at a particular depth where the defect is lying. So this is how the display in this case of B skin. Next, so the next one is a C skin, and in this case, uh, we have a plan type 2D view as you shown in that particular image on that particular slide. The 2D view of the defect In order to generate that, this has to be plotted either on an XY plotter. So the data is recorded by an XY plotter, or it can be also shown on a computer screen, which is superimposed on the plan view of the sample. So so for that we record the data, and then either we can plot it on XY plotter or can show it on a screen, which will be superimposed on the plan view. And that is how this plan type view will be generated. But in order to create that particular view, in this case the data has to be recorded as a function of each of the reflecting interface. So unlike the previous cases where you simply send the ultrasonic wave and get an echo from the defect or from the other surface, in this case you need to collect the echo as a function of a position of the reflecting interface. Okay, so in order to do that, you need to move the probe in a particular manner, as you see in that particular image. If we have a sample, okay, and so you show that side view and the top view of that particular sample. Okay, so if we want to that collect the data as a function of the position of each of the reflecting interface, so in order to do this the scan a following particular manner. So that manner, if you see in that particular image, that is a zigzag manner like this. So if the defect, if you see that 2D view, it may be shown in that particular image where we write there C skin. Both the image you can see. So you have collect the echo as a function of each of these reflecting point. So 2D type of view are in the display, and it finally display on the system. So you see the scan view, how it look like as you see in on that image. So it will shown up that point, top view of the plan view, and you will see a profile of this defect at a particular location. So in this case the echo are recorded as a function of each of the reflecting interface, and with that you will get a scan and a view as you shown in that particular image. So these are the different type of scans or view displayed in the case of ultrasonic testing. So dear student, for any query please write me on my mail id rohitsau87@gmail.com, rohitsahu87@gmail.com. Thank you. Thank you. To be continuing in the next session. Stay safe, stay home. Take care.